Managing private workloads in the cloud requires secure, predictable network access. Traditional approaches with public IPs can expose services unnecessarily, creating complexity in routing and security. So, what if cloud compute instances could access the internet reliably without public IPs while inbound traffic is controlled and workloads remain isolated? Hello everyone, I'm Sanskriti Harmuk, a developer relations at Vultr, and in today's Tech Talk, we will explore how Vultr's NAT Gateway enables secure outbound access for private instances and manages inbound traffic using port forwarding, all while maintaining enterprise-grade network isolation. So, to see it all in action, let's dive right into it. Before we get into NAT Gateway, let's first understand why VPC-First Networking matters. VPC-First Networking means the virtual private cloud becomes the default and a standardized network boundary for compute resources. So instead of treating networking as an optional layer, every instance is placed into a clearly defined VPC where IP addressing, routing, and isolation are consistent by design. This makes network behavior predictable as environments scale across regions and deployments. From security and operations standpoint as well, this model reduces attack surface by limiting unnecessary public exposure and minimizing configuration shifting. Private workloads stay isolated by default, segmentation is enforced at the network layer, and access is made explicit rather than implicit. Building on the VPC first model, Vultr NAT Gateway provides a managed way for private instances inside a VPC to access the internet without assigning a public IP address. Outbound traffic from multiple private instances is translated using managed SNet, allowing shared egress through a single gateway while keeping individual workloads private and isolated. Each NAT gateway is backed by one reserved public IP, which becomes the consistent egress identity for outbound traffic and the entry point for any explicitly configured inbound access. Inbound connectivity is enabled through optional port forwarding and firewall rules, giving fine grained control over what traffic is allowed. All of this is centrally managed within the VPC boundary, simplifying operations while maintaining strong security defaults. Now let's walk through what actually happens on the wire. When an external client makes a request to an application endpoint like app.example.com, the request resolves to NAT Gateway's public IP and reaches the gateway first. The NAT Gateway then checks whether a matching port forwarding rule exists and whether the traffic is permitted through firewall policies. If those conditions are met, the request is forwarded to private application instance and ports inside the VPC. This allows inbound access to specific services while keeping underlying instances unreachable directly from the internet. On the other hand, when we make a request from a private instance to an external service, the traffic never goes directly to the internet. The request first leaves the instance with its private IP and is routed to the NAT gateway, which acts as VPC's egress point. At the gateway, source NAT is applied, translating private source address to the gateway reserved public IP before the traffic is sent out to the internet. Now that we understand how traffic flows through a NAT gateway, let's look at how this works in practice. In this demo, we'll create a VPC with a NAT gateway and deploy a private instance without a public IP. We'll first verify outbound internet access from the private instance through the NAT gateway and then demonstrate how inbound access is selectively enabled through port forwarding and firewall rules. This will show how private workloads can remain isolated while still supporting controlled ingress and egress traffic. With the networking model and traffic flow in mind, let's start by setting up the foundation for the demo by provisioning a virtual private cloud on Vultr. To do this, open the Vultr customer portal, navigate to Products, expand Network section, and select VPC Networks. Here, click Add VPC Network. You can start by providing a name to your VPC network. During creation, you'll see two options: creating a VPC intended for instances with public IP or creating a VPC designed for private instances behind NAT Gateway. For this demo, we'll select the option to create a VPC with a NAT Gateway. Further, choose the location where your instances will be deployed. For network configuration, you can either specify a custom IPv4 CIDR by providing network address and prefix size, or proceed with the automatically assigned private IP range. Once the settings are in place, click Create VPC Network. This provisions a fresh VPC with an attached NAT gateway, ready to support private instances for controlled ingress and egress connectivity. Let's click on it to open its management page. Here, apart from the usual VPC details, you'll also see NAT gateway information, including its reserved public IP address and gateway's private IP, which occupies .1 address from the VPC subnet. .1 addresses are generally reserved for gateway and serves as default route for instances within the subnet. Our next goal is to deploy a private compute instance that will live entirely within the VPC. To do this, switch to the compute section under products and click deploy server. Here, start by selecting the appropriate compute type based on your workload requirements. Then choose a region where your instance will be deployed. It's important that this region matches the VPC we created earlier, as VPC networks are region specific. Then, pick a compute plan that matches your application's CPU, memory, and storage needs. Once the plan is selected, move to Configure Software section. Here you can choose a standard operating system, deploy marketplace application, or select a custom ISO image. For this demo, we'll proceed with an Ubuntu 24.04 operating system. In the server settings, you can attach an SSH key for secure remote access, configure a startup script for automated provisioning, or apply a firewall group if needed. These options help standardize access and configuration as instances scale. For easier identification and management, it is also advisable to provide a hostname and label for your instance. Now, for networking configuration, we will select private instances behind NAT Gateway. Once selected, Vultr will automatically list all existing NAT Gateway enabled VPCs available in the same region. If a suitable VPC doesn't already exist, then you can create one directly from this screen by clicking Add VPC Network, providing a label, and choosing either automatically assigned or custom IP range. In our case, we'll proceed with the VPC we created earlier. You can also select any additional instance features like limited user login based on your security and operational requirements. Once everything is configured, review the deployment summary and click Deploy. Vultr will then provision the private instance inside the VPC without a public IP and attach it to the NAT gateway for controlled outbound connectivity. Once the instance is deployed, it is automatically assigned a private IP from the VPC subnet. This IP is used for internal communication within the VPC and for routing traffic through the NAT gateway. You can also confirm this assigned private IP by opening Instance Details and switching to the Settings section where VPC network and private address are listed. Alternatively, you can verify this from the VPC networks page as well. Just open the VPC we created earlier. Here under attached notes, you will see private instance listed alongside NAT gateway, each with their assigned private IP. This confirms that the instance is fully contained within the VPC, does not have a public IP, and relies on NAT gateway for any external connectivity. To validate this behavior further, let's test outbound connectivity from the private instance. There are several ways to access the instance, including using the Vultr console, connecting it through Bastion host within the same VPC, or accessing it over a VPN. You can select the method that best fits your environment and access requirements. Once inside the instance, let's simply check the public IP address it uses for outbound traffic by running curl ifconfig.me. Even though the instance does not have a public IP, it can still reach the internet. The NAT gateway performs source network address translation, replacing instance's private IP with gateways reserved public IP address before sending the request externally. This is similar to how a home router handles outbound traffic, allowing the instance to remain private while still accessing external services for updates and API calls. Now let's look at the inbound traffic flow and how controlled exposure is achieved without assigning a public IP to the instance. Inside the private instance, we'll first install a simple web service to act as our application endpoint. Once Nginx is installed, we allow HTTP traffic at the operating system level. This step is important because the instance firewall must explicitly allow traffic to the service port. Now, to confirm that the service is running locally, let's send a request to the local endpoint. This succeeds, which tells us Nginx is listening on port 80 and OS firewall permits the traffic. Next, let's attempt to access the service from an external source, such as your local machine or a public instance, using NAT Gateway's reserved public IP address. This request fails, and that is expected. At this point, the traffic cannot reach private instance because inbound access through the NAT gateway is blocked by default. The gateway has no context on how to handle incoming traffic unless explicit rules are defined. Without port forwarding rules, the NAT gateway does not know which private IP and port should receive the request. So, to fix this, let's switch back to the Vultr customer portal and configure inbound access. On the VPC management page, scroll down to NAT port forwarding section and click Add Forwarding Rule. Start by giving the rule a name, then select a protocol, TCP in this case. Further, specify an external port. We'll use port 8080 here so that the inbound traffic to the gateway on port 8080 can be mapped to our application. Next, provide the internal IP address of the private instance and set the internal port to 80, which is where Nginx is listening. You can also provide an optional note here for reference. Once everything is configured, click Save Changes. With port forwarding rule in place, the gateway now knows how to translate inbound traffic. Let's also add a firewall rule. First select a protocol and then specify subnet and subnet size. For this demo, we'll allow traffic from anywhere, but for production grade systems, this could be restricted to specific IP ranges. Further, provide a port. You can also add an optional note again here for reference. Once everything is done, click Save Changes. Now let's switch back to the terminal and retry the request again, but this time with port 8080. As we can see, the request succeeds, which reflects that the traffic reaches the NAT gateway, passes the firewall check, is forwarded to the private instance on port 80, and Nginx responds as expected. You can also open the same endpoint in a web browser and see the default Nginx page. In this way, Vultr's NAT gateway enables private instances to securely access the internet while remaining isolated from direct public exposure. It gives you precise control over what traffic enters and leaves your VPC without assigning public IPs to individual instances. Everything you have seen in this demo can also be automated and managed programmatically using the Vultr API, making it easy to integrate NAT gateway configuration directly into infrastructure as code workflows and CI/CD pipelines. For more information, refer to our product documentation linked in the description of this tech talk. To summarize, we have seen how Vultr's NAT gateway allows private instances within a VPC to access the internet securely through managed SNET while also enabling controlled inbound access through port forwarding and firewall rules. If you're ready to try this yourself, then create a NAT gateway enabled VPC on Vultr and deploy private instances within it today by claiming $250 in free credits on a new account using the promo link attached in the description below. For any questions or to share your experiences configuring NAT gateway and VPC networking, join the discussion on the Vultr community forum. Thank you so much for tuning in. We hope this tech talk helped you confidently manage private workloads, control traffic flows, simplify networking operations using NAT gateway on Vultr.